We hear about AI learning all the time, but have you ever wondered how that actually works? It's a really delicate process, and sometimes the very signal that's supposed to guide the learning just breaks down. Today, we're going to dig into something called the unstable gradient problem. It's this fascinating issue that can either make a neural network's learning signal fade to a whisper or explode into a chaotic shout. So let's jump right in. Okay, so first things first. At its most basic level, a neural network's job is to learn. Simple as that. It looks at a ton of data, it makes a guess, and then it adjusts itself to get better next time. The real magic, though, is in how it adjusts. Think of it like this. The network has millions of tiny little internal dials. We call them weights, and it's constantly fine-tuning them until it starts getting things right. And this whole adjustment thing, it happens in a really cool loop.
So here's that learning loop in action. The network makes a prediction. Then it checks how wrong it was. We call that the loss. And then comes the magic part, calculating the gradient. The gradient is everything. You can think of it as a set of instructions, or maybe like a tiny arrow that points the way towards being less wrong. It's the signal that tells every single one of those little dials, those weights, hey, you, turn a little to the left, or you, turn a little to the right, all to make the next guess just a little bit better.
All right, so the gradient is basically the network's teacher, right? It's the guide leading it to the right answer, but what happens when that guide starts giving really bad directions? What if its instructions are so quiet you can't even hear them? Or what if they're so loud, they're just meaningless noise? Well, that's when this whole amazing learning process can completely fall apart.
Okay, let's tackle the first and probably most famous symptom of this problem. It's called the vanishing gradient, and this is something that tends to hit the very first layers of a deep network the hardest. The ones that are the farthest away from the final answer.
So here's the problem in a nutshell. As that learning signal, the gradient, travels backward through all the layers of a deep network, it can start to shrink. And by the time it gets all the way back to those earliest layers, the ones looking at the raw data, that signal can be so incredibly faint, it's practically gone. It has, vanished.
And remember, the whole point of that gradient signal is to tell the weights, those little dials, how to turn. But what if that signal is just a tiny, microscopic whisper? Well, the adjustment it makes is going to be just as tiny.
Yeah, it's pretty much like trying to steer a giant cargo ship by, blowing on the rudder. You're just not going to change course. It's not going to work.
So what happens? The weight barely moves from where it started. It's pretty much frozen solid. And that's the heart of the issue right there. The weight gets stuck. And when it's stuck, it can't learn and it can't help the network get any better. And if those crucial early layers can't learn, the entire network suffers. These are the layers that are supposed to learn the really basic stuff, like spotting edges or colors in a picture. If they're stuck, the layers that come after them have nothing to build on. The whole learning process just grinds to a halt. So, okay, we know what happens, but now let's talk about why it happens. It turns out the root cause of this whole mess is hiding in the very way these networks learn, in a process called backpropagation. And really, it all comes down to a long chain of multiplication.
Now don't worry, we're not going to get bogged down in the super heavy math, but the key thing you need to know is this. To figure out the gradient for any given weight, backpropagation multiplies a whole chain of numbers together. It starts at the very end of the network and works its way backward. So think about it. If you're a weight in one of the very early layers, that chain of numbers you're multiplying is going to be really long, right? Way longer than the chain for a weight in one of the later layers. And that is where the trouble begins.
Just think about what happens when you multiply a bunch of numbers that are all less than 1. Even if you take a number like 0.9, which is pretty close to 1, and you multiply it by itself over and over and over, it shrinks down towards 0 incredibly fast. And that is exactly what's happening to that gradient signal as it travels backwards through a deep network. It just gets smaller and smaller with every step until, poof, it's gone.
But here's the thing. A vanishing signal is only one side of the coin. If we use that exact same logic, that chain of multiplication, we can run into the complete opposite problem.
So, what do you think happens if all the numbers in that chain are bigger than 1? Well, just like you'd expect, the result doesn't just get bigger, it grows exponentially. It explodes into a ridiculously huge number. The learning signal goes from that helpful whisper to a deafening, totally useless shout. And the result of this exploding gradient is that the update to the weight is just massive. So instead of taking a small, careful step toward the right answer, it takes this giant leap and completely overshoots the target.
It's like trying to park a car and just slamming on the gas. You don't just miss the spot, you probably make things a whole lot worse.
So, okay, we've seen signals that just fade away into nothing, and signals that explode into total chaos. But what's really crucial to get here is that these are not two separate problems. Nope, they're two symptoms of the exact same underlying issue, a fundamentally unstable learning signal.
And this comparison really lays it out perfectly. Look, the cause is the same for both, that long chain of multiplication during backpropagation. But the outcome, totally different, and it all depends on whether the numbers in that chain are big or small. If they're small, the gradient vanishes and learning just freezes up. If they're large, the gradient explodes and learning goes completely off the rails.
And that brings us to the absolute core idea of this whole explainer. The real problem isn't the vanishing gradient, and it's not the exploding gradient. It's the bigger, more general problem of unstable gradients. The learning signal is just too volatile, too unpredictable, and that makes training a deep network reliably incredibly difficult.
So, why should you care about any of this? Because for decades, literally decades, this was the problem. This was the massive wall that stopped progress in AI. Researchers just couldn't build the really deep, powerful networks that we have today because their learning signals were just too darn unstable. Overcoming this instability was the breakthrough that unlocked pretty much everything we see now, from incredible image recognition to the large language models we all use.
Which, of course, leaves us with one final and really crucial question. If these learning signals are so naturally prone to either vanishing or exploding, then how in the world do we build networks that can keep them stable and under control? Well, answering that question is the challenge that has driven so much of the incredible innovation in this field.